Hello, and welcome to the first session of the 2021 Mining Law Summit. I'm David Hammond, a semi-retired geologist, engineer, and applied mineral economist. And I'm continuing to be involved in many aspects of minerals needed for energy supply demand transition and our national security and new electronic technologies. Today, we're going to be talking about a few of the critical minerals and materials. Joining me in that effort is Dr. Rod Eggert, a longtime professor of mineral economics and a deputy director of the Critical Minerals Institute at the Colorado School of Mines.
Dave, thank you very much for having me. It's great to be here.
Okay. Our task today is to introduce and define critical minerals, materials, and in a minute, Rod is going to make that distinction a little bit more definitive. But also we're going to try and describe why they are so critical to global energy production and use, and also to national defense and security, as well as being pretty much indispensable to our modern technology-based civilization. In keeping with the theme of this conference, we'll try to focus as much as we can on the procurement and upstream side of the critical mineral supply chain, although the material requirements of the downstream device production end, where the important technologies and devices, products that are critical to energy and defense, which really represent the actual driver of demand for these critical minerals. Things can get pretty complicated. So to begin with, let's do some definitions and characteristics of critical minerals. So what are the critical minerals and materials? Well, there are some very fundamental characteristics that apply to all of the critical minerals. And those are critical minerals, materials provide critical functional properties to a product or a process. They also are in our current environment very difficult to substitute for in the products or the functionality that you're trying to make or achieve. And number three, they involve risky supply chains. And when we talk about risky supply chains, we could be referring to the physical existence of the input materials, the ores, the minerals, or it could be talking about risky situations along the supply chain where the input ores or minerals are converted to a final usable product or an intermediate product that needs onward processing. Or we may be referring to just the location of all of these components of this supply chain. There's some additional attributes that don't necessarily apply to all or to each and every one of the critical minerals, materials, but they are very important for some of them. Things like where a critical, one of the, and I'm going to abbreviate here, CMs just to cover it so I don't have to say the same thing every time. CMs frequently are produced as byproducts from the extraction of other metals or minerals. At the present time, a lot of this byproduct material is not recovered from mills and smelters, refineries, just goes out into the waste stream, although that is obviously changing as the number of these materials, these CMs, become more critical. Second, for a great many of them, the processing, the extraction process technologies can be quite challenging, getting the raw material, the ore, into usable form. Compared to what most people are familiar with in the mining, global mining industry, the tonnages involved for a number of these critical materials are relatively small, at least at the present time. Order of magnitude almost differences, where we might be talking about copper as on the order of, say, 20 some million metric tons of primary production per year. For some CMs, we might be talking a few thousand tons. And for some at the present time, it's on the order of, well, perhaps hundreds of tons for global consumption. So that kind of leads to the next point. Some of these critical materials are produced from very small scale mining operations. And that in turn has, as you might imagine, a number of aspects that we need to think about. And lastly, and again, this is not an exhaustive list by any means. For, again, a number of the CMs, at the present time, the global and our domestic resource information, how much is there out there and where is it at, is not quantified anywhere near it is for some of the major metals, such as nickel, aluminum, copper. So the criticality of a mineral material to the US can also be illustrated on this next slide, where we, and this is from the US Geological Survey, every year for, I'd say the past couple of decades, the USGS has put out once a year a report and an illustration of how dependent the US domestic economy is on imports of specific materials. And I know that this graph is a little hard to make out, but think of it this way. We start up at the top of it, and we have a few very low use, relatively low use minerals: arsenic, asbestos, cesium, and fluorspar. And the blue line across from each one shows what are the percent of our import dependency. So you'll see for the first 15 or so of the minerals on this list, the US dependency is 100%. Down around the middle of the chart, you'll see numbers bringing on the order that illustrate greater than 75%. And then falling off the bottom, minerals that we are much less dependent on here in the US for our needs, things like bromine, zirconium, lead, vermiculite. On the right-hand side, the countries that are the primary exporters of the materials to the United States are shown. So for say cesium, the main supplier to the US is at 100% is Canada. And so you can, the point that needs to be made, though, in looking at this list, is there sure are a lot of China and Russia and countries we may not have the best comfort with in as being suppliers going forward. So on this slide, that point is illustrated just a little more definitively. Here by color, we can have, shows the number of commodities off of that list that various countries serve as suppliers to the US. So this is where the source of these materials for us. And the more red the color, the higher the number of minerals that we are dependent on that country for our supply. So you can easily see here that China represents one of our major supplier of materials, of minerals, followed by Canada, and then Russia, Australia, and Brazil, and South Africa. So while we've shown on the USGS exposure to import or import dependency of minerals, let's now go and put the critical adjective in front of it and then talk about those in a little more depth. Over the last decade or so, US policymakers have put a lot of work into critical minerals and materials from the perspectives of defense and the economy, particularly on the energy side, and conversion of our electric system to more green or less carbon basis. Much of this has been done by the DOE, Department of Energy, Department of Defense, and the USGS. And with the end result that critical materials, CMs, are formally defined and identified and published at various times in the federal legislature. So here is the list as defined by the the U.S. government of the critical minerals as you can see, May 2018. Rod, would you like to go into the present list and maybe talk a little bit about its evolution, the parties involved? Before you do that, can you give us some insight on the mission, history, and activities of the Critical Minerals Institute, which I know has been and continues to be involved in obviously all of the aspects of our critical minerals dependency.
Dave, yes, happy to do that. Happy to jump in now and both talk a little bit about this list and first discuss the Critical Materials Institute. The Critical Materials Institute, of which I am Deputy Director, is a research consortium funded by the U.S. Department of Energy. The mission of the research and development is to develop technological options that will help secure supply chains for selected materials that the Department of Energy has prioritized for emerging energy technologies. And so some of the technology development focuses on diversifying and enhancing primary production, produce more in more places, in other words. Part of the research and development focuses on wasting less of what we do produce. So R&D focused on improving manufacturing efficiency and enhancing recycling and reuse. And the third area of technology development is, you might call, using less, developing substitutes for similar functions of materials, but using elements that are not on the list. So that's the Critical Materials Institute. We can talk about technology development as a public policy later in the session, but let's return to this list. So this list is the official US government list of critical minerals. This list of 30-some elements or families of elements reflect materials that satisfy two characteristics. First of all, there is a significant degree of net import reliance for the United States. And second of all, there is lack of diversity in the supply chains. And so, Dave, you talked about import dependence previously. That's a useful initial indicator of riskiness of a supply chain, but it's only part of the story. If we have diverse import sources, a supply chain may be no more risky than if we have a single vulnerable domestic source. And so this list reflects both characteristics, import reliance and lack of diversity in the supply chains. And it reflects risks from the perspective of US manufacturers and customers, manufacturers that use these materials in the components and manufactured systems they build, and then the customers, all of us who purchase automobiles and refrigerators and electronic equipment. So you can see it's quite a range of materials, and it simply reflects import dependence and lack of diversity in supply chains. Now, we've used the phrase critical minerals and critical materials somewhat interchangeably, and that's because in the discussion, at least discussions I'm involved in, these phrases are used somewhat interchangeably. The Department of Energy uses the phrase critical materials because it is primarily concerned about the risks to the development and deployment of emerging energy technologies, and its materials that the wind turbine and electric vehicle manufacturers use. They purchase materials, whereas the US Geological Survey is more comfortable with and typically uses the phrase critical minerals because of the upstream focus of the Geological Survey. But it's really an issue of risky supply chains, ranging from or starting with resources in the ground and ending with the manufactured systems of materials, the final products that we purchase. So one perspective that this list reflects is risks to US customers, whether households or manufacturers who purchase materials. Another aspect of risk is more of the risk from the perspective of the Department of Energy, and that is the fear that lack of certain materials puts the development and deployment of emerging energy technologies at risk. And if we could have the next slide, please, I will illustrate that point. So this slide, very complicated, but let's walk through it step by step. The key point is that the mineral needs vary significantly from one technology to another, and we have a range of materials that are important. And this matrix or this table is an attempt to illustrate the range of uses where the mineral resources are essential. So in the columns, we have the materials or elements or minerals, copper, cobalt, and so on. In the rows, we have various energy technologies, starting with solar PV, wind, hydro. CSP is concentrating solar power, and so on. And the color codings or the shades of gray in the circles represent the degree of importance of a particular material for that technology. And so if we look at copper on the left and aluminum on the right, they are important in anything dealing with electricity, electronics, and electrification, which is a major theme in the decarbonization of the energy economy. Moving to the right from copper, we have cobalt, nickel, and lithium, which are essential in lithium-ion battery technologies, the renewable batteries that at the moment and for the next couple of decades at least, if not longer, will be the battery technology of choice in electric vehicles. REEs, further to the right, represents rare earth elements. They are important in state-of-the-art magnets, which in turn are essential for the most efficient electric motors. And electric motors in turn are critical for offshore wind turbines, electric vehicles, and battery storage in many electrical generation activities. Moving further to the right, chromium and zinc are important as specialty materials in specialty steels that have important uses in the wind towers and hydro facilities and concentrating solar and so on. So specialty steels that use small amounts of chromium and zinc to enhance the properties of the steel. PGMs, platinum group elements or metals, very important and essential, irreplaceable at the moment at least, in fuel cells and the technologies that we envision for the hydrogen economy. So a range of uses in a range of energy technologies. If I could have the next slide, please. So here we have a sense of the magnitude of need for the elements on the previous slide and a couple of others in emerging energy technologies compared to the conventional or traditional. So focus your attention on the upper part of the diagram that's labeled transport, and the horizontal bar represents kilograms per vehicle. The first row represents the electric vehicle or a typical electric vehicle. And just below that is the conventional vehicle. And these are the kilograms per vehicle on average. What is it, 30 compared to 200? So what is that, a 6 or a 7-fold increase in the requirements of the set of elements on the right? It's not all the materials in the automobile, but it's the elements on the previous slide and a couple of others. So it's copper in the electrification, the wiring of the automobile. It's lithium, nickel, manganese, cobalt, and graphite in batteries. It's chromium and molybdenum and zinc in specialty steels, rare earth elements in the magnets, in the electric motors, and so on. The bottom part of the figure does a similar assessment for electric power generation. And so at the bottom of the lower part of the figure, we see coal and natural gas powered electricity generation. So the material requirements for the materials listed on the right-hand side of the figure are on the order of 2,000 to 3,000 kilograms per MW, per megawatt. And if we go up then in the diagram, you see the much more significant requirements for nuclear, solar photovoltaics or solar PV, onshore wind, and offshore wind. And to put this into context, other than copper and perhaps nickel among the list of materials on the right-hand side and zinc, these are materials for which the existing market scale of production and consumption is reasonably small. And so this increase in material requirements raises the question, will the speed of capacity expansion for the minor elements listed on the right keep up with the increasing demands for these emerging energy technologies. So here's riskiness from the perspective of the net zero or the decarbonized economy. Will we have the materials at an acceptable price in a time frame to align with goals for deployment of electric vehicles and various clean energy technologies. So there's an energy sense of critical minerals and materials. There's also, moving beyond this slide, you can imagine a defense, a military perspective on critical raw materials. And there is a part of the US Defense Department that focuses on military needs. And then finally, if we think about consumer products and the digital economy, there also are a set of elements that are very important for the increasingly digitalized economy. So we have risks from different perspectives. So you might say criticality is situational. Criticality depends on who you are and where you are and when you ask, or criticality is in the eye of the beholder, which reflects the different aspects of riskiness for different materials, and the fact that different customers and different manufacturers and manufacturing sectors and technologies have somewhat different material needs. David, so at this point, maybe I can turn it back to you and we can begin our discussion of the multidimensional nature of criticality, or the different dimensions of the riskiness of mineral and material supply chains.
Thanks, Rod. I think that was a superb discussion of coverage of the order of magnitude on the needs for some of these critical materials at a global scale, and looking into the future. And by the way, we've extracted, borrowed some of these slides from a very good report by the IEA that came out in April of this year, that focuses on the importance of a lot of these major and minor materials in the decarbonization of the globe. And the name of that is The Role of Critical Minerals in Clean Energy Transitions. And for those of you that are interested, that is available on the web, no cost to anybody. So when you look at the number and the diversity of the critical minerals necessary for these various applications and usages, there are many differences in how and where they are geologically sourced, how they're processed into useful economic products. And there are even different levels of criticality when you consider the supply sources and the tonnages that are required or will be required. So how does, say, CMs differ from other important mineral commodities, which most of us and lay people would be more familiar with, such as the major metals, aluminum, copper, lead, and zinc? Rod, you got some comments on that?
Yes, I'd be happy to comment on that. So think of, let's compare, let's generalize and talk about two classes of mineral commodities, major metals and minor metals. Most, but not all, of what people refer to as critical minerals or materials, I would classify as minor metals. Minor in the sense that the overall annual tonnage produced and consumed is reasonably small. So in an extreme case, if we look at scandium, one of the elements on the U.S. critical minerals list, which is used in specialty metal alloys, especially in lightweighting, annual world production is something like 10 tons a year. Compare that with, Dave, you mentioned copper, probably 20 to somewhere in the 20s, 20 million tons. So 10 tons versus tens of millions of tons per year. If we look at lithium, we're talking about 1 to 200,000 tons per year. If we look at rare earth elements, it's about 200,000 tons per year. So the scale of production and use is much smaller for many of the critical materials. I would also use the word vitamins and spices to describe many of the critical materials, in the sense that vitamins in small quantities provide essential properties to you and me, Dave, when we have breakfast in the morning. Or spices in small quantities provide that special flavor associated with, pick your own favorite cuisine, you know, French cooking or Italian cooking or Peruvian cooking. It's the spices, small quantities, essential properties, special properties that are important in modern engineered materials. And then a point you raised earlier, Dave, a third point of difference. Many of the minerals termed critical are produced largely, or in some cases solely, as byproducts or in association with other relatively more important materials from the perspective of the mine operator or the metal producer. And so if you look at tellurium, which has annual demand of several hundreds of tons per year, but has important uses in certain solar photovoltaic materials, tellurium is produced almost exclusively as a minor byproduct from the waste product from copper smelting and refining. And so the availability of tellurium, which couldn't stand on its own as a mine, commercially, at least without prices that are much, much higher than they are today, and much higher than one could imagine being absorbed in solar power manufacturing. Tellurium is dependent on copper. And so the availability is a function not just of the price of tellurium, but the economic attractiveness of copper mining. Now, the good news is that in the case of tellurium, there's a lot of unrecovered tellurium at existing copper smelting and refining operations. The bad news is that once one runs out of that, if demand increases more significantly, then it would take a significant price increase to call forth additional quantities of this byproduct. It's a similar story as well with other byproduct host or major metal or principal product pairs. And lead's an interesting example as well, because it is the principal source of certain things like germanium, which have important electronic and electronic materials uses. Well, as lead over the last several decades has fallen out of favor and has been prohibited to be used in everything but lead acid batteries associated with conventional vehicles, the amount of process waste from which the germanium can be extracted has fallen. So I would say quantities, the scale of production, the vitamin spices argument, and the prevalence of byproduct production are three distinguishing characteristics of many of the critical minerals and materials.
Well, thank you, Rod. What this really comes about suggesting then is that the producers going into the future of a number of these critical minerals are going to be quite different from today's major mining companies, given the scale of production and its profitability. Growing critical material importance over the last two decades has certainly indicated that is the trend by the upsurge in junior mining companies that are getting involved in materials such as the rare earths and lithium. And this brings in a whole host of other considerations. I think policymakers and investors need to think about as these junior companies are dependent primarily on public markets for their financial resources. Investors need to be concerned about the business models of these companies. Some of them, and it's no secret, junior companies tend to focus on shall we say, the financing of their exploration activities in trying to enhance the characteristics of a mineral discovery that they may have on their portfolio. And a lot of times their ultimate objective, their exit strategy is not to be creation of an actual mine and production from therefrom, but basically sell out to a larger entity that would actually proceed with the development. This brings into the question if some of these minor metals, in fact, a lot of them, are not attractive financially to a major mining company, such as a Rio Tinto or BHP, because they don't really contribute a lot to anything significant to their bottom line. What are going to be the mining companies that actually do produce, build the mines and provide the supply that are going to be required in increasing quantities as we move forward with this decarbonization and continuing issues, or continue needs for consumer electronics and defense. So there's a number of considerations or aspects that need to be thought of by the financial communities and policymakers when we look at dependency on these smaller firms that are getting into the critical material space. Items such as what's their capitalization, what's their ability to finance moving forward. Does the little company have the appropriate management expertise to deal with these oftentimes very complex mineralogies and more importantly the very hard technology that's required to process these minerals into their marketable form. The production technology for major metals like copper, iron, they've been around, for thousands of years and have evolved to very efficient and very economical production process, smelting, refining technologies. So that's not the same in space for things like rare earths and some of the other minor metals, where the technology is still in a stage of development. And in general, a lot of these are, for a lot of these metals, the technology is much more complex. In the case of rare earths, instead of having one or two, a primary metal and possibly a byproduct metal, you're dealing with sometimes anywhere from 5 to in excess of 10 individual rare earth elements that you want to extract. And so this turns into a very complex distillation process, if you will. And the chemistry for this, every company seems to have its own approach. They try to develop their own, oftentimes proprietary technology, which may or may not be proven in the end. And the last point, when you start looking at smaller companies who are attempting to actually move forward to build a mine, is do they have the level of environmental responsibility and expertise that one would expect in today's world, in which a level at which major mining companies have adopted and actually perfected over the last few decades. So these are some of the things that we need to look at for the standpoint of getting dependent on these smaller companies to provide these materials at global scale. And there's associated SEG regulatory aspects involved, and a number of other considerations. Your thoughts on this, Rod?
Okay, Dave, you raised a number of issues there. I won't try to comment on all of them, but let me selectively comment on several. First, from the perspective of investors or the investment community, a couple of important issues with respect to critical minerals. First, in many cases, these markets are somewhat opaque, which means it's difficult for entities outside of the actual producers and users to develop a complete picture or a sufficient picture of the sector to be confident about investing. It's not an insurmountable challenge, but it does present a barrier, which then in turn represents an opportunity for those investors that can overcome that barrier. But opaqueness or opacity of the market or lack of transparency is a challenge. Another consideration for investors is technology risk or end use risk. There's a lot of buzz, has been the last several years, about vanadium as a potential battery material in what are called vanadium flow batteries that possibly could be very important in stationary storage, or the storage of energy from electric power, from solar and wind, the oft used expression, the sun doesn't shine and the wind doesn't always blow. So we need efficient battery technology to store that energy for when we demand it. And vanadium flow batteries have a potential significant use. If that use takes off, the demand for vanadium could grow several times given the current level of demand in specialty steels. But if that use does not take off, vanadium will continue along the way it has based on the demand for other uses. So that's a perspective from investors. You talked about producers and the types of companies involved and the technological challenges. If one looks at rare earths and lithium as two specific examples, the existing players in those markets, by and large, do not involve any of the well-known mining and metal producers. It's a different set of companies. And in part, I think that reflects that in the case of rare earths and lithium, mining is almost not so much an issue as the midstream processing and the manufacturing of specialty chemicals of different forms, which requires a different type of expertise than being efficient in mine planning ore reserve characterization, crushing and grinding, and initial stages of beneficiation and metallurgical processing. So there are somewhat different skills, which suggests, and almost certainly there will be some different companies involved in the supply of critical minerals than the traditional Rio Tintos, BHP Billiton, Anglo-American, Freeport, and so on. Having said that, the big companies have become attracted and I think have dipped their toes in the water, especially when it comes to battery materials. Rio Tinto has some initial small-scale efforts aimed at entering the lithium market for lithium-ion batteries. BHP Billiton is a nickel producer, and so it's understandable that they would be interested in taking advantage of their existing nickel expertise as nickel's use grows as a battery material. The final thing I would say in terms of different perspectives and considerations is the consideration of the manufacturer that arguably, and in some cases certainly is, at risk due to the risky supply chains. And what can a manufacturer do? What might it do? What should it do? And I think a manufacturing company, a Toyota or a Tesla or a General Electric, in effect has to think of this as buying insurance. One of the developments, insurance against supply chain disruptions, recognize that the manufacturers have dramatically benefited from globalization and the specialization in the location of production of minerals over the last 50 years. Rare earth production is concentrated in China. Lithium resource production is concentrated in Chile and Australia. Lithium chemical processing capacity is concentrated in China. So we have Chile, Australia, and China in really specializing in different parts of the lithium supply chain. And that's brought benefits to manufacturers and customers, lower prices. But lower prices come with somewhat greater risks because of the lack of diversity in the supply chains and the distance associated with the supply chains. And so what is a manufacturer to do in terms of insurance? And I use insurance in inverted quotes. It's not as if they can buy an insurance policy, but rather they undertake different commercial strategies aimed at making their supply chains less risky. So one can imagine strategic alliances. We've seen Tesla do that with several battery suppliers. There are offtake agreements where a Toyota, for example, guarantees that it will buy a certain fraction of a new mine's output. And that offtake agreement allows the mining company to go to the markets, the financial markets, and raise the capital because the investors are confident that at least some of the output has a guaranteed market. In some cases, manufacturers are co-funding investments in mining and mineral processing. In theory, we could have vertical integration where Tesla would become a lithium miner. I think that's not likely. There are benefits to specialization, and I think the other less dramatic forms, short of vertical integration, where Tesla becomes a lithium mining company or General Electric becomes a rare earth mining company, that's not going to happen, I don't think.
I would agree with you on all those points, Rod. It reminds me of the need that someone in Washington, I believe, said recently that something like digging a hole in the ground isn't that hard. Well, actually, when you look at the entire supply chain, no, it is hard. And the question would be, are the companies such as a Tesla that might look at involvement in the upstream production of their needed materials, will they be able to recognize the right expertise, technical expertise, to successfully conduct an operation on the upstream side? I think that would be a question that investors need to think about.
David, I have one more thing there. One thing that some of the larger manufacturers do, I think of as long-term insurance, and that is they undertake R&D to eliminate or at least significantly reduce their need for, say, rare earth magnets. So Siemens and General Electric and Toyota all have initiatives underway to develop magnets that don't require what are perceived to be risky rare earth magnets.
Absolutely great point on that, Rod. So I think we also might consider for a minute on the dependence of the domestic U.S. Manufacturing on outside supply sources. Could we ever actually achieve relative independence from these supply chain risks by developing resources here in the U.S., but in the context of the geologic permissibility of a lot of these materials that we need aren't, some of them aren't found here in the U.S., or they are, if they exist, they may be in jurisdictions that are environmentally sensitive, that's difficult to get social license to produce on, of course, subject to the ever-changing regulatory environment for mining across the U.S. Now, do you think we could ever be self-reliant on regards to our critical materials needs?
Well, I would say first, our ability to become self-sufficient varies somewhat from mineral to mineral. But I think more importantly, I would argue that self-sufficiency is an illusory goal. What we want and what we should focus on are diversified and secure and sustainable supply chains. Part of the story is additional domestic mineral production, but that's only a part of the story. And so a lot of I would focus on a combination of reshoring, as sometimes has been stated, relocate activities back to the United States. That's part of the story. Part of it's near shoring, get stages in the supply chain closer to us, and that might mean Canada or Mexico. And I would also say work with allies to create diversified supply chains, not 25 diversified supply chains, but something that reduces the risk of a single point of failure in a supply chain that could be geopolitical in nature, it could be weather or climate related, it could be natural disaster related, it could be the shipping disruption risk. And it's really the security of the supply chain as opposed to the goal that everything should be domestic that I would argue is the appropriate way to think about this.
Yeah, and then of course, over the top of this is the need that we do want to have lowest cost suppliers of a lot of these materials to for the economics of the utilization on them.
That's right, Dave. There's a balance between desire for low costs, lowest cost at the moment, and the security from disruption. And how do you balance that?
Very good question that policymakers need to be giving serious thought to, and increasing amount of time on it as we move forward. So time to wrap up, and we might want to take a moment to think about the implications for the present and future development of these critical materials and minerals from the perspective of the conference theme of the future of mining law. Couple thoughts on that. Mineral royalties and taxation impact future supply of any material, any resource commodity. And so how royalty and taxation structures, particularly in the developing world, which are definitely going to be part of the supply solution equation, as those evolve and change, and we certainly know a lot of those have high volatility in the changes. How is that going to impact provision of these materials? Are jurisdictions, governments going to try to institute taxation regimes, revenue streams out of it that could impact the security or the desirability of supply from these countries? Of course, there's also the question of will appropriate management, expertise for to address the complexities of the production of a lot of these materials. Will it keep pace with the needs for the supply of these? Globally, right now, we have issues on just the number of mineral specialists, mining engineers, geologists, metallurgists to keep up with the needs going forward. And the fact of it has to be recognized that some of these rare earths, for example, and some of the other materials do have some very serious environmental aspects that have to be kept in mind and provided for remediation in the process. So a lot of things that we might have to keep in mind. There's also the possibility that if things get too dangerous as far as the supply chain, of government subsidization of critical materials resources and processing. An example might be rare earths, which may lead to some sort of government supported facility to produce, to extract into metal and metal alloys the oxides that might come from a variety of different rare earth sources. So Rod, do you have any concluding thoughts before we sign off here?
Well, Dave, in the last minute or so, you've raised, I think, at least 4 additional topics that would be worthy of a 45-minute session. We don't have time for those today, but I agree. Mining royalties and fiscal systems are important. My general view there is that the broad forms of those need to be governed by sound principles of public finance, and then maybe in special circumstances, one-off, modified or adjusted to accommodate the critical minerals or materials theme. The government subsidization, again, that's a tricky area to get into, and other than my agreeing with what is, I would hope, is common sense, we want efficient systems for permitting and evaluating the desirability or the pre-production approval of new mines. We want efficient transparent processes pre-production. We want sound environmental policies, and we want good and appropriate, I would say, involvement of local communities in which mining operates. And so the ESG, environment, society, and governance piece is very important. Again, I don't think that should be driven by critical minerals, but rather critical minerals, and that discussion needs to reflect and consider ESG considerations. I think that's all from me.
Okay, well, those are some great thoughts, Rod. And so I hope everybody's gotten at least an introduction to this, if you haven't already, some involvement with these critical materials, and that this will serve as a backdrop to the discussions, the ongoing sessions of the conference. So we'll turn it back to the conference MC, and we'll say goodbye for now. By the way, if anybody has some questions or wants to discuss any of the things we talked about in a little bit more detail, I'm sure Rod and certainly myself, we are more than willing to have a chat with you. So thank you very much.